let us continue to look at some more aspects of phase response. What we had seen earlier was if you cross a 0 on the unit circle, the phase response will change by pi. Let us get some more feel for this. So, we have a 0 on the unit circle and this is at an angle of theta. Let us consider each of e to the j omega at omega equal to theta minus and at omega equal to theta plus. So, we are looking at a point here and at a point here. So, this is theta minus, this is theta plus, epsilon close to theta. When you compare the distances to all other zeros and poles, then when you go from theta minus to theta plus, will the distances to all the other poles and zeros, will those change much or will there not be any change? There will not be any change because you are moving from theta minus to theta plus. So, as far as every other 0 and pole is concerned, the change will not be much, it will be a very negligible change. The change will be negligible for both the products of the distances as well as to the change in the angle as far as all the other poles and zeros are concerned. Therefore, we will now try to relate the frequency response at theta minus and at theta plus. So, we want to look at each of e to the j omega at theta equal to theta plus, and we want to relate this to the frequency response at theta minus. As far as all the other poles and other zeros are concerned, nothing much is going to change. However, when you consider the 0 at theta, and since the 0 is on the unit circle, when you cross the 0, you are going to acquire a phase change of pi. Therefore, the frequency response at theta plus is related to the frequency response at theta minus. The only difference is it will acquire a phase change of pi, otherwise everything else remains the same. And e to the j pi of course is minus 1, and hence this can be written as the frequency response at omega to theta minus, but with a minus sign. Therefore, what you can infer from this is that when you cross a 0 on the unit circle, you acquire a sign change. So, this is an important point. So, crossing a 0 on the unit circle causes a sign change. Let us now get a feel for this with a specific example. Suppose you have each of n to be 1 between minus cap n to plus cap n, then we know that each of e to the j omega is sine 2n plus 1 omega by 2 by sine omega by 2. We have seen this quite a few times before. We have also seen the z transform of this. So, this is h of z is 1 minus z to the minus 2n plus 1 by 1 minus z inverse. Therefore, this has roots equally spaced on the unit circle for the numerator, the zeros, and it has one non-trivial pole at z equal to 1, which we have seen before gets cancelled. Therefore, as a simple example, this could be the pole 0 plot for a certain value of n. Now, again we have seen this geometric interpretation before, we are revisiting this, but now we are focusing on a point that is related to the idea of acquiring a sign change when you cross a 0. So, when you plot h of e to the j omega, which is this function, and we know what the shape is from the geometric interpretation. If you are here on the unit circle, you will have a certain frequency response, and then when you go towards the first 0, the frequency response will drop, and when you are on the 0, this frequency response at this particular point will be 0, and now you are crossing this. Remember, we are actually plotting h of e to the j omega, which we can plot. There are no issues, because in this particular case h of e to the j omega is this real valued function. When you cross this 0, the frequency response becomes like this. Let me just complete the picture. And now you see, crossing this 0 has now caused a sign change. The frequency response was positive here, and once you have crossed the 0, the frequency response has now become negative. Therefore, this is the intuition behind crossing a 0, acquiring a phase change of pi really means a sign change. And of course, this is true for every 0 that you cross. The same frequency response can also plotted in a slightly different manner. In this case, because this was real valued, you can plot it like this, but you can also plot it in the usual sense, and what we have been used to is, we have been used to plotting magnitude response and phase response. Therefore, if you now plot this particular frequency response, that is magnitude for this particular case, then the response will look like this. So, this is magnitude. What about phase? So, between these 2 points, h of e to the j omega is a positive quantity, non-negative quantity, and the phase of a real number that is non-negative, the phase is 0. Therefore, the phase response is like this, 0. And now, when you consider this interval, the amplitude is negative and the phase corresponding to a negative number is pi, and hence in this interval the phase response is pi, and by convention we plot the phase for a negative number when omega is greater than 0 to be plus pi, because equally well you could have marked this as minus pi. And similarly, when you look at the next lobe which is positive, again the phase response is 0, and for the next negative going lobe the phase response is again pi. And because this is a real valued sequence, magnitude response is even, phase response is odd. Therefore, once you have plotted the phase response for omega greater than 0 to be like this, you have to complete the picture from 0 to minus pi as the one that is consistent with an odd symmetric plot. Therefore, in this region you will have minus pi, again 0, and again minus pi, and so on. So, this is the same frequency response that is plotted as magnitude versus frequency and phase versus frequency. In this particular example, because it was real valued, you can also plot h of e to the j omega just by itself. On the other hand, if it were complex, you need to plot real part versus frequency and imaginary part versus frequency, or you can plot magnitude versus frequency and phase versus frequency. Yeah, question.
You could very well do the other way, like the odd symmetric plot we did. Flip it, right?
Yeah, so you mean to say, so this being minus pi and this being plus pi is, yeah, so that is why I had mentioned that by convention for omega greater than 0, you show this as plus pi. It is just a convention. Yes, what you are saying is correct. This could as well be flipped and still it will be consistent. Yes, you can, in this particular case you can make it even symmetric, but because the sequence is real valued, in general the phase response is odd, we make it as an odd symmetric sequence. So, what you are saying works only for this particular case, not in general. All right. So, what we have seen in the discussion of phase response is when you cross a 0, the phase change is pi. Therefore, when you plot magnitude versus frequency and phase versus frequency, the phase will jump by pi whenever you cross a 0. Now, let us look at another representation of frequency response where there are no jumps of pi. Suppose you had this particular sequence, suppose you had g of n which was 1 from 0 to 2n, and you can easily see this is nothing but h of n minus cap n, where h of n is the h of n that was shown in the earlier example. And now you can easily see that the frequency response g of e to the j omega is using the delay property e to the minus j omega cap n, sine 2n plus 1 omega by 2 by sine omega by 2. As far as magnitude response goes, nothing changes because the delay has introduced just a phase factor, magnitude response remains the same, and hence this is as before. So, this is magnitude of the new sequence identical to the earlier case. Now, as far as phase goes, this particular term e to the minus j omega n, if you look at the phase of this term alone, this is a linear phase term with slope omega is, the value is minus omega n. So, this is a linear phase term. So, if you just focus on this alone, then the phase response will be like this. But the overall phase response given this magnitude response is the phase response due to this term and the phase response due to this term. Therefore, the overall phase response is the addition of this phase response to this linear phase term. And if you look at this, so between the case where you are in this region, nothing changes because you are going to add 0. However, when you come to this spot, then you acquire a jump of pi, and then the linear phase term continues. So, this is how the phase response looks. So, this is the odd symmetric completion of the figure, and this jump is a jump of pi. All right. Yeah. Is there a question? Yeah. So, the phase response is just this minus omega n, and so this is a linear function. So, that is why I have drawn this black curve, which is linear with that particular slope, with slope of minus n. So, phase response is not limited to be between minus pi and pi. We are going to actually come to that concept in a minute. The frequency can be anything, but as far as the signal is concerned, you replace frequency by frequency mod pi because the resulting signal is no different. But when you are looking at the phase response, it is precisely given by this term, which is minus omega n, and minus omega n is exactly this. There are no issues here, but we are going to the point that you have in mind in a minute. So, this is the overall phase response for this given magnitude response, and this shows jumps of pi. However, there is another representation in which the phase response will not show jumps of pi. So, to see how that comes about, we will write each of e to the j omega as a of omega times e to the j phi, whereas previously we have been writing the frequency response as magnitude times e to the j phase angle, and by definition this is non-negative, whereas in this representation A of omega is a real valued function, and we will see that this is really phi of omega, and for systems with rational transfer function, in this representation you can show that this will be continuous. And again, considering the example we have just now seen, we have seen g of e to the j omega as e to the minus j omega cap n times sine 2n plus 1 omega by 2 by sine omega by 2, and in the modified representation of the frequency response, this is A of omega, and this happens to be phi of omega, and the difference is A of omega I had mentioned is now a real valued function. The main difference of course is now this can take on both positive as well as negative values, and hence in this representation, if you now plot the frequency response as a product of amplitude response times e to the j phase response, where phase response is now continuous. Now A of omega has this shape. Main difference is it now can take on negative values as well, and the corresponding phase response is just this term, which is linear. Whereas if you represent this in magnitude times e to the j phase angle, whenever you cross a 0, you are acquiring a phase change of pi. A phase change of pi is a sign change. The magnitude being non-negative cannot take on negative values. Therefore, the sign change that crossing a 0 causes has to be absorbed in the phase response as a jump of pi. Whereas in this representation, when you cross a 0, you acquire a sign change. That sign change is absorbed in the amplitude response because it is now real valued, and hence the phase response is continuous without any jumps of pi. Let us again continue on the theme of change of pi when you cross a 0 by looking at this particular example. So now you have, say, R of n, which is now h of n convolved with h of n, where h of n is the all ones sequence between minus n to plus n. Therefore, the all ones sequence between minus 1 and plus 1, if you convolve a rectangular pulse with itself, it will become a triangle. Therefore, this will be the envelope of R of n. So, really if I want to plot the stem plot, it will be like this, and this is between minus 2n to plus 2n. And as far as R of z is concerned, so this is nothing but h of z whole squared, and the corresponding frequency response is sine 2n plus 1 omega by 2 by sin omega by 2 whole squared. If you now plot the pole 0 plot, of course, there will be a certain order trivial pole, and then you will have zeros on the unit circle, but the difference in this case will be that, what can you say about the zeros? So, they will be second order, yeah, repeated zeros, that is right, or second order. So, now rather than simple zeros, you now have double zeros. Now, let us see what this means. In terms of frequency response, so here at omega equal to 0 you have a certain value, and then as you approach the first 0 on the unit circle for positive omega, the response drops and then keeps dropping, and then when you hit the 0, you are now crossing this double 0 rather than a single 0. Each 0 will cause a phase change of pi. When you cross a second order 0, the total phase change will be 2 pi, and a phase change of 2 pi is no sign change, and hence the frequency response will become 0 and again go back up. So, this is how the frequency response will look. So, what this says is, this says that if you cross an nth order 0, the phase change will be n times pi, and depending upon whether n is odd or even, you will either have a sign change or no sign change. So, this is along the lines of the question that was raised. In general, the angle h of e to the j omega, which you can denote it as theta of omega, is not constrained to lie in any interval. And the example for this is the example that we had seen earlier, which triggered the question. So, there we saw that the phase angle was minus omega n, because it was e to the minus j omega n times sin 2n plus 1 omega by 2 by sin omega by 2. Therefore, theta of omega was minus omega times cap n. Therefore, if you plot theta of omega versus omega, this is the plot you will get. And another notation for h of e to the j omega, which I have mentioned before, is ARG, which stands for argument. So, this is this h of e to the j omega, and this is not constrained to lie in any interval. Suppose we restrict the range of the phase. Suppose we require the phase angle to belong to this interval minus pi to pi, then this is called as the principal phase, or other common term is wrapped phase. And the notation that is used is ARG, capital ARG, and this must lie in this interval. Therefore, if you now want to plot the phase response for this particular example, if you want to plot the principal phase, so this is between minus pi and pi, say, when it becomes more negative than minus pi, you add as many multiples of 2 pi that is needed to make the final value lie between minus pi and pi. So, this is how the wrapped phase is. So, clearly in this interval, which will correspond to a value here, you need to add 4 pi to make it between minus pi and pi. So, this is how the wrapped phase is. This is basically phase angle modulo 2 pi, and the reverse process is called phase unwrapping. Therefore, given this sawtooth waveform, whenever you see a jump of 2 pi, you will add or subtract enough multiples of 2 pi to make the final curve continuous. Note that one important difference is we have seen jumps of pi before, whereas in this case this is a jump of 2 pi, whereas the jumps we have seen before the phase response are jumps of pi when you cross a 0 has an odd order. And as I had mentioned before, going from ARG to little arg, this is phase unwrapping. All right. And this might seem very simple. All you need to do is add or subtract enough multiples of 2 pi so that the resulting curve is continuous. But the problem is not as simple as this, and there are research papers that have worked on this, because you could have some ambiguities in this problem, and a phase unwrapping algorithm by Jose Tribole, 1977, I think. That is one of the most widely used algorithms for phase unwrapping, and there have been some improvements to that algorithm ever since that came out. So, this is not as simple as what it appears to be, but for our simple problems, just adding or subtracting multiples of 2 pi will cause phase unwrapping, and the resulting phase will be continuous. Let us see a MATLAB example to illustrate this. So, this is the elliptic filter that I had used earlier to showcase the difference between IIR and FIR filters, roughly having the same frequency response, but the elliptic filter was of much lower order, 5th order in this case, whereas the FIR filter required order 32 to meet the same frequency response. So, that same filter I am using. So, let me now compute the frequency response, and I will compute this over 1000 points from 0 to pi. Now, what I am going to do is I am going to show the angle. Let me first show the pole 0 plot. So, this is the pole 0 plot. Therefore, you can expect when you go along the unit circle, when you hit this 0, you can expect a phase jump of pi. So, let us verify that. So, here let me plot the phase response, and this is angle H, and let me plot the angle from 0 to 0.5, because this is real value. It is enough if you plot this from 0 to pi. So, since I have taken 1000 points, so this is the phase response, and this is the wrapped phase response. So, this phase response keeps on decreasing. At this point, it is trying to become more negative than minus pi. Therefore, wrapping will cause you need to add enough multiples of 2 pi so that the phase always stays between minus pi and pi. Therefore, this jump is a jump of 2 pi, because you do not want the phase response to go more negative than minus pi or more positive than plus pi. Therefore, at this point you add 2 pi and you reach this point. Therefore, this jump is 2 pi, and then the phase response keeps on decreasing, and now you hit the first 0. Therefore, this jump is now pi when you cross the first 0 on the unit circle, and then the phase response keeps on decreasing. Remember, I had mentioned to you that by convention MATLAB uses a jump of plus pi for omega greater than 0. So, this is indeed omega greater than 0. Here I have plotted f rather than omega, I have plotted omega by 2 pi. At this point, again you encounter the second 0 on the unit circle. So, by convention you have to jump up by pi. If you jump up by pi, you will exceed the minus pi to plus pi range. Therefore, you actually jump down. That is the reason why you are jumping down here, because this is a wrapped phase. So, this is the overall phase response. It is now staying between minus pi and pi. Let us now plot the unwrapped phase, and for ease of comparison, let me plot this as plot number 1. So, MATLAB has everything that you want. If you want to unwrap, just say unwrap, it will unwrap, right. So, MATLAB can do anything short of eating your lunch and writing your quizzes. MATLAB can do anything you want. MATLAB and Google together solve all of life's problems. Okay. So, this is the unwrapped phase. So, now you see that this jump of 2 pi is gone, because you have unwrapped. So, now it keeps going. Now, you have hit the first 0. Unwrapping will not eliminate jumps of pi, it only eliminates jumps of 2 pi, and you have now jumped up, because this is a 0 on the unit circle and we are looking at positive frequencies. And again, after this jump of pi, you keep going, and then you hit the second 0, and now again you are jumping up by convention, and you keep going. So, this is the unwrapped phase, this is the wrapped phase. Okay. So, this tells you the difference. As far as the signal itself is concerned, it does not matter whether you use wrapped phase or unwrapped phase, because it is e to the j phase angle. Any angle or angle modulo 2 pi does not make a difference, and hence as far as the signal is concerned, using wrapped phase or unwrapped phase does not matter. However, there is one area that is called Kepstral processing, and there you have to work with the unwrapped phase. If you use the wrapped phase there, you will get the wrong answer. There you take the phase angle and deal with the phase angle as a separate function. You process the phase to get some more information out of it, and in those cases you definitely have to deal with the unwrapped phase rather than the wrapped phase. So, there are cases where unwrapping is important, but that is outside the scope of this course. Let us look at the phase response of a resonator, just to get some more feel for how phase response works. Remember, recall the phase response of a single complex pole. The phase response of a 0 was like this. This is the first thing that we started off with when we were looking at phase response of a single complex 0. This 0 was on the real axis, so that is why it went to 0 at that particular point. For a single complex pole, the phase response for a pole is just the negative of this. Therefore, this is how the phase response will be. And as far as a resonator goes, so this is how the pole 0 plot of a simple resonator looked, if you recall. So, at r e to the j theta and r e to the minus j theta, you had two poles, and if you looked at the phase response of each pole, you will see that the response will look like this. So, this is no different from this, only that the point at which it crosses 0 is now located at theta. Here it is at omega equal to 0, because in this particular example we were looking at the pole lying at theta equal to 0 or on the real axis, positive real axis. And if theta were not 0, all it will do to the phase response is shift it to the left or to the right by whatever amount. So, this is the phase response of this first quadrant pole. The phase response for a second quadrant pole will be like this. And the overall phase response is the addition of these individual phase responses, and you will see at omega equal to 0, each will contribute equal and opposite values. Therefore, at omega equal to 0, you will have 0. Similarly, at pi and minus pi, you will have equal and opposite contributions, phase response will be 0. And when you cross a 0, the phase will change rapidly. Therefore, so this is how the overall phase response will look, and the most rapid change will occur at plus theta and minus theta. And this is no different from what we saw for the system that had two zeros on the unit circle. Remember, when we were looking at zeros on the unit circle, we had something like this, right? this is no different from that. In the zeros case, this is precisely linear because 0 is on the unit circle, whereas in the pole case you cannot have poles on the unit circle, therefore you will have a response something like this. So, this is the phase response of a resonator. Let me quickly see if I can show this in MATLAB. Therefore, if I have say R equal to 0.9 and so the numerator is 1, denominator is 1 minus 2 times R cos, let me have theta as pi by 4, and 1 minus 2 R cos theta z inverse plus R squared z power minus 2. Therefore, the other term has to be R power 2, and then let me evaluate this at 2000 points, all right, and then I will use FFT shift of this, and then I will plot angle between minus 999 to 1000 divided by 2000. I have 2000 points, and then I will plot angle of H. I really should have given whole. So, this was the rough sketch I had plotted, and this in on my notes, and this is the exact sketch. So, at omega equal to 0 you have the phase response going to 0, and the most rapid phase change happens when around the region where you cross the pole. At omega equal to 0 and at f equal to 0 and f equal to minus half and plus half, the phase response goes to 0, and this is how the overall phase response is for a resonator. So, this is the exact plot. What I had plotted in my notes, sketched in my note was just rough. So, this is the exact plot for R equals 0.9 and theta equal to pi by 4. And closer R is to 1, the more rapid will this phase change be, and deeper the pole is inside the unit circle, gentler will this change around this region will be.